Okay, so now we're going to talk about descriptive statistics again, with spending a little bit more time on various sorts of measures of central tendency and variability. Again, measures of central tendency and measures of variability or dispersion. As we recall from our last set of slides, measures of central tendency tell us what's average or typical for a given case in the distribution of a variable. So it is a single value that can describe what's going on in a variable to figure out what the most central position of that variable is. And it's a good way of reducing in our variable into something that's more digestible or manageable, right? So, for instance, we have this example of average life expectancy in the US. We can calculate or gather information on every person in the US and their age, but that's hundreds of millions of cases. To make it more manageable, we often say, well, what is the average age? Well, what's the average age given a specific race or ethnic background? Right here, we see the average age is 76.1, but for each racial group, we see that it's a little bit different. Our average life expectancy, I should say. So the mode is the least sophisticated of these measures of central tendency. Right? It's found, or it's the most frequent value. It's found by taking all of your values, arranging them chronologically, and then selected the value that shows up the most often. And it's important to note that more than one mode is possible, right? It can be bimodal, trimodal, multimodal, meaning that there are many modes, many numbers that appear over and over and over again. So let's say we had a range of scores, 92, 88, 74, 92. These are maybe scores on a final exam. What we'd have to do is arrange them and figure out which ones are appearing the most. Here we see 74 appears 3 times, 88 appears twice, 92 appears 4 times. So here we would have a single mode, and that is 92. 92 is going to be our mode, or the value that appears most often. It's important to note that we can also calculate the mode from nominal data. And so here we take a frequency table, a frequency distribution for people's self-identified religion. And we see Protestant is 128 people, Catholics people identify as Catholic 57 times, 10 people identify as evangelical, so on and so forth. Here, the mode would be the most frequently occurring category. For here, or for us, it's Protestant. Protestant has the highest value here. The median is a little bit more sophisticated, right? And the median can be calculated, well, the mode can be calculated for nominal, ordinal, and interval ratio variables. The median is a little bit more sophisticated, or that is, it requires higher levels of sophistication, right? Because we want to figure out what the middlemost value is, we need to be able to order those values, right? And if we want to order the values, we need to have a level of measurement that is at least can be ordered, that is at least ordinal. So always represents the exact center of a distribution, so such that half the numbers are smaller and half the numbers are greater than the median. So for this first example, if we have an odd number of cases, we order those values and then figure out which one's the middlemost value. We sort of like cross each of them off from end to end, and the middlemost value here is 87. For even numbers of cases, I'm sure you've done this in your algebra classes before, we order them like we would for odd number of cases, and then we take the 2 middlemost values and we calculate the actual average of those 2 middle cases. So the 2 middle cases here are 87 and 88. Say 87 and 88 plus 88 divided by 2, which is 87.5. Right, so we're just trying to find the middlemost value. So these variables must have categories or attributes that can be ordered. And then finally, the mean. The mean is not only the most commonly used measure of central tendency, but it's the most sophisticated, which means it requires the most sophisticated level of measurement, which means that if you're trying to calculate the mean, you need at least interval ratio level variables. It's the arithmetic average that is commonly used. To compute it, you add up all the scores and divide by the total number of scores that you're using. So value 1 plus value 2 plus value 3 all the way to value n divided by n, and that gives you the mean. It's important to note that this mean is susceptible to extreme scores. This means if you have one or a few highly extreme scores, so high extreme scores or low extreme scores, when you calculate that mean, it might pull that value up. If you have a few high extreme scores, it'll pull that mean down if you have a few low extreme scores. Okay. So let's take this example here. We have 1, 2, 3, 4, 5 different values. We have 15, 20, 25, 30, 35. To take the mean, 125, that's the sum of all these numbers divided by 5, is 25. Also, we know that the median is 25. For these two, for this group, it's 15, 20, 25, 30, and then it's not 35, it's 3,500. The median is still 25, right? Because it's the middlemost value. But the mean is now all of that summed together, which is not 125. It's 3,590 divided by 5 is 718. So we see by just throwing in one value that's extremely high, it pulled that mean way up. So the mean and the median will only be the same when the distribution is symmetric, right? And that means that you have similarly high and similarly same amount of high and low scores, right? When a distribution has some extremely high scores, that indicates a positive skew, right? So you can think of something like income. Income is something that has a positive skew because you have a bunch of people on the low end or the middle end, and then you have a very, very few people at the top end of income making millions of dollars a year. So if we take the average of that, it's going to pull that average up. That means it's going to have a longer, what we call a right tail. So a tail on the positive side of the distribution, meaning a positive skew. This also means that we will have a mean that is greater than the median. Right? When we have a distribution that has some extremely low scores, we're going to have a negative skew. So the tail will be on the left-hand side, a left skew, and then the mean will be lower than the median. And so here are some examples of what that might look like. So symmetry and skewness in distributions is important. So skewness refers to how far the distribution deviates from symmetry. So a nice bell curve, right? A normal distribution. Distribution can be positively skewed or right skewed or negatively skewed. And skewness refers to, like I said before, that position of that longer tail of that distribution. So if the tail's on the left, it's left skewed or negatively skewed. So like I said before, a classic example, positively skewed or right skewed is income or salary, where high-end earners provide a false representation of what's average or typical the income or salary. Negatively skewed, a good example of that is age of retirement, where few people retire young, but most people are retiring at older ages. So we have a symmetrical distribution or a normal distribution, also known as a Gaussian distribution or a bell curve. We have some right skew or positive skewness here, the longer right tail. We have negative skewness here, the longer left tail. Measures of dispersion or variability. So whereas we have measures of central tendency that tells us where the average or typical scores are, measures of variability or dispersion give us more information about the spread or the clustering around that mean. We use standard deviation, range, and variance. We can think of variance as sort of a stepping stone towards standard deviation. A good measure of dispersion should describe the average deviation of the score. So how far, on average, these scores are from the center or the mean of the distribution. And so as you include more values, this standard deviation or measure of dispersion should get smaller, right? Because adding more cases, but the variability, all of these cases start filling in more of the variability that exists. You can think of like an empty bell curve where one person's at the end, one person's at the middle, one person's at the uh, low end. But as you start adding more cases, people will start to fill in various spots on that distribution. Not everybody's going to be on the high end, not everybody's going to be on the low end, not everybody's going to be in the middle. There's going to be some mix. So in that first example with 3 cases, the variability measure or measure of dispersion is going to be big because these cases are far from each other. As you include more and more cases, they'll be closer and closer to one another. They'll be more clustered, sort of built off what we know as the central limit theorem. So I have this example. Suppose a manager wanted to evaluate the performance of 2 delivery truck drivers. They look at each driver's mean time per delivery, number of times they spent on each delivery divided by the total number of deliveries, and find that the means of these 2 drivers are very close to each other. You might assume that they're doing the same work, right? But measures of dispersion or measures of variability tell us a little bit more about what's going on with that average, right? They reveal additional information about the spread of these delivery times around the mean. For driver A, they might have scores that are more grouped around the mean, so they have more consistent scores, less spread. Whereas driver B might have more scores on the high end, so longer delivery times, and more scores on the low end, so short delivery time. So there's more variability there. Therefore, for driver B, we'd have a higher variability score. With driver A, we'd have a lower variability score, right, because they're more clustered together. So standard deviation, as I referred to it before, is the average deviation. So most commonly used measure, the average deviation from the mean. So we take the deviation, which is what we call raw score deviation, how much one person's score differs from the mean. And then we take an average across all of these scores. So it's similar to calculating an average. We sum up or add up all of these deviations and divide by the number of cases. But because the sum of deviations is always 0, we need to get rid of the negative, so we square this. So we usually do the sum of squared deviations to increase this value. So we get rid of our negatives. So we look, somebody's value is 10 and the mean is 30. 5 scores with a mean of 30. Somebody's value is 10. 10 minus 30 is negative 20. But we know that the mean is somewhere in the middle. It's a balancing act. And think of a fulcrum sort of balancing a seesaw. It's always going to be in the middle. So the deviation scores are going to balance each other out. So here we have negative 20 as a deviation score. Negative 10, somebody got 30, so 30 minus 30 is 0. 10 here and 20 here. If we sum all these values, it's going to be 0. How do we figure out how much people are on average deviating? Well, we do this thing, a nice little trick of squaring these deviation scores. And that gives us positive values. So we have 400, 100, 0, 100, and 400, which gives us sum of the squared deviations, which is 1,000. Now we need to take the average of this number. Right? So how do we take the average? Sum of the squared deviations, we divide that number by sample size. But importantly, we do an adjusted sample size. So rather than dividing by n, we divide by n minus 1. And it gives us a measure of dispersion called variance. Variance, sometimes we use it, a lot of the times we don't. And that's because it's in these weird square units. And we did that to get rid of our negatives, so we didn't have the sum resulting in 0. So to get it back into our original scale, we take the square root of variance, and that gives us our standard deviation. So this value, take the square root of that. That's variance, so we take the square root of that, and it gives us standard deviation. So, like I said before, standard deviation will be higher for more diverse distributions and lower for less diverse distributions. Another way of saying that is if there's more spread from the mean, standard deviation will be higher. If there's less spread or more clustering around the mean, standard deviation will be lower. When standard deviation is 0, that means that every case in the sample is exactly the same score. There's no spread. around the mean. Um, Typically, we use things like standard deviation, but also range. Range is important for telling us what the highest and lowest values are for our distribution on the variable.